Now, where we ended off the last video was in noticing that when we asked the computer if 0.1 plus 0.1 plus 0.1 was equal to 0.3, the computer said false. We then engaged in a discussion where we learned that the computer can only allocate a finite number of spaces of precision to representing decimal numbers. So it's clear then for numbers like pi or 1/3 that have infinite decimal representations that we're going to lose something when we represent them in the computer. What is still very perplexing is why a decimal number that terminates in a finite number of digits like 0.1 should be causing some type of approximation error within the computer. And there is a perfectly good explanation, but it's a little bit deeper, but also very interesting. And it comes with the compiler and that translation from machine language and that translation from current modern day mechanisms to binary numbers, which are long sequences of zeros and ones. Now, throughout history, the metric system and humans currently in general, we use a base 10 number system, mostly because we have 10 fingers, and so our current number system places a heavy value on the number 10. This hasn't always been so throughout time and history, and different cultures and at different moments in time, there were other number systems that were valued for different purposes. One example of that is that we use dozens to talk about number of eggs. We use a base 60 number system when we're talking about time. And computers are very heavily a base 2 number system. So in the translation from a base 10 number system to a base 2 number system, which the computer uses, something is happening. And what's really happening is that the number 1/10 super integral to a decimal number system and has this beautiful finite simple representation in base 10, it actually has a very complicated representation in base 2. And in fact, when we take the number 1/10 and we translate it to a binary number, it becomes the way 1/3 is in base 10, where it has that infinite need for perfect representation. And that's the reason behind this round-off error. What I think is absolutely fascinating is that this whole concept was studied by ancient Egyptians thousands of years ago, way before there was ever any thought of computers. And the reason that they were studying it was because of beer. I'm being a little bit presumptuous there. The reason that they were studying this was because of the way in which the ancient Egyptians would partition what's called a hecat, which was their unit of volume used to measure things like grain and bread and beer. But beer was in ancient Egyptian culture, and it was in fact a form of payment for a day's work. It was thought of not entirely for its drug-inducing purposes, but mostly for its sustenance purposes. It was thought of along the lines of grain and bread for sustenance. But the ancient Egyptians were very focused on unit fractions, which makes sense. Concepts of fractions are complicated, and unit fractions really have this more simplistic interpretation of we have one thing and we're dividing it into how many pieces. So ancient Egyptians very much liked unit fractions. Where the hecat comes into play is that we would look at fractions of a hecat for distribution for a day's work. So you could have something like a half of a hecat, but then you could have half of a hecat, and that successive halving. And so when distributing parts of a hecat, it was always in this sense. It was always a unit fraction, so a 1 in the numerator, and then the denominator needed to be a half, or a half of a half, or a half of a half of a half. In other words, it had to be a power of 2. And so this whole interesting area of study in ancient Egypt was just what different types of fractions can be represented as a sum of these parts of a Hecate: halves, fourths, eighths, sixteenths. So one example would be a fourth plus a 16th plus a 32nd. Another example could be a half plus an eighth. All of those specific types of fractions were special fractions to the ancient Egyptians because they could be represented naturally and had this interpretation that was meaningful to them. Interestingly, that problem of ancient Egypt is exactly the problem in modern day of which decimals have a very easy and natural representation when translated into binary numbers. And one thing that the ancient Egyptians knew was that 1/10 could not be expressed in this way. And that's the reason behind this error. 1/10 cannot be represented as a finite sum of parts of a Hecate, and therefore it is doomed to have round-off error in the compilation process from high-level programming language to binary number.